Testing, testing. Hello, Math 0092. We are beginning with Chapter 1 on page 2 with introducing standard notation, place value significance, and expanded notation. We're looking at page 2 at the bottom and defining a digit. A digit for us is a number 0, 1, 2, 3, 4, 5, 6, 7, 8, or 9. Those are the digits. We use the digits with our place value significance. For large numbers, digits are separated by commas into groups of 3, which are called periods. So here we have the ones period, 1, 2, 3. We have the thousands period, 1, 2, 3. Millions period, 1, 2, 3. Billions period, 1, 2, 3. And trillions period, 1, 2, 3. And by the way, these periods continue infinitely. Within each period, there is the ones, the thousands, and the millions, the billions, and the trillions, and so on. To understand the number of people attending the Broadway musicals in our table above, we're looking at the table and the type of performance, looking at musicals. We have a large number representing the attendance. The first period is the ones, the second is the thousands, and the third period is the million. Placing these digits in our place value significance within the period, we have 1, 1, 3, 6, 2, 7, 3, 2. And we would read this number as 11,362,732. So again, with respect to each period, we read the number and the period name. So 11,362,732 ones. On page 3, we're looking at examples trying to decipher certain digits and their place value. So in example 5, we're asked, in each of the following numbers, what does the digit 8 mean? So in this number, I'm going to find the digit 8 and in what position is it located? What is its place value significance? Well, here's the ones and here's the thousands period, and it's in the ones category of the thousands, so it was 8,000. Next number is 8, 7, 2, 3, 4, 2. And again, we're still trying to determine what the digit 8 means. So we're going to find the digit 8. Here's the ones period and the thousands period. In the thousands period, we have the ones and the thousands. So that's 800 in the thousands period. Another example, 6,328. Determine what the digit 8 means in this number. So I'm highlighting the digit 8, and it's in the ones category, the ones that ends in the hundreds. It's in the ones of the ones period. So it's 1. Example 6, websites. In July 2017, the total number of active websites on the World Wide Web was 8,225,423,000.
79. What digit names the number of the 10 millions? So my number is 1, 2, 2, 5, 4, 2, 3, 0, 7, 9. Use the ones, the thousands, the millions, the billions, and we're looking for what digit names the number of the 10 millions. Well, here's our millions period. Ones, tens, hundreds, and we're looking for 10 millions. So the digit 2 would be the number representing the 10 millions placeholder. On the top of page 4, a number of families assisted in Africa was 959,734. This number is expressed in standard notation. We write expanded notation for this number as follows. So our standard notation, standard notation. Now notation means just a format, just as we highlight Minnesota West in blue, Minnesota West in italics, Minnesota West in underlined, it's still Minnesota West. This standard notation represents our number in what we typically would expect to write a number in standard form. But we could expand. So expanded notation is just another format representing the same number, but formatted differently. Expanded notation, we have our ones, our thousands, and we have the 1 position, the 10 position, and the 100 position. So this is the 900 thousandths position. Plus, we have the 5 10 thousandths position. Plus, we have the 9 thousandths position. Plus, we have the 7 hundredths location. Plus the 3 tens position. Plus the 4 ones. And so expanded notation is expanding the place value significance of the digit to represent the standard notation of the number itself. Both represent the same value. Example 7 on page 4. Write expanded notation for 1,776 feet, the height of One World Trade Center in New York City. So we have our number 1,776, and that would be standard notation. And we're supposed to write expanded notation. So I have my ones period, and I'm in the thousands period. The ones is represented, there's no tens, no hundreds. So I have the 1,000 position plus the 7 hundredths position plus the 7 tens position plus the 6 ones position. Standard notation, typically the way we expect to write a number, we can write it in its equivalency value with expanded notation, itemizing each digit with respect to its place value significance. Also on page 4, converting between standard notation and word names. Word names are often used as we pronounce a number or we speak the name of a number. A word name for 56 is 56. So here's our digit and place value significance. So standard notation and its word name. The word name for 56 is 50 hyphen 6. Word names for some two-digit numbers like 36, 51, and 72 use hyphens. 72. Write the word name as 72. 70-2. Now that's correct to use the hyphen. You must use the hyphen in homework and testing. But something like 17, we have a word for 17. The word is 17. So our digits 1, 2, 3, 4, 5, 6, 7, 8, 9, we have a word name for them. 1, 2, 3, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. And then we have 32, which would be 30 hyphen 2. 46, 40 hyphen 6. So be sure to use the hyphen appropriately. 121. A word name is 120 hyphen 1. Example 12 on page 5. Write a word name for 46,605,314,732. So example 12, we write there's a 1,000, billion, period, and we're using the ones and the tens. 40 hyphen 6 billion, 605,314,730 hyphen 2. In section 1.2, section 1.2 on page 9, we're talking about defining our whole numbers and natural numbers. The set of natural numbers. The set of natural numbers is thus set 1, 2, 3, 4, and we continue with that sequence. It's our counting numbers. 1, 2, 3, 4, 5, 6, 7, 8, 9. And we first go and we develop to count our points, to count our numbers. So we're talking about the set of natural numbers. That's 1, 2, 3, 4, 5, 6, 7, 8, and it continues infinitely. The whole numbers.
the set of whole numbers, as we get a bit older in our development, we begin to add and understand the value of zero. So we have a set of whole numbers, which is 0, 1, 2, 3, 4, 5. So the natural numbers are a subset of the whole numbers. Here we have the natural numbers as a subset of the whole numbers. So we build upon the natural numbers to create the set of whole numbers. And I just think of the whole numbers. Here's a big whole. It is our zero value. Make sure you understand the set of natural numbers and the set of whole numbers, and that the whole numbers include a zero and the natural numbers. Well, then we begin to use these numbers in arithmetic ways. So the first thing we want to do is add whole numbers. So when we add 878 plus 995, we'll use our calculator. I'm using a TI-85 calculator. At 878, I use my plus symbol. Find your plus symbol on your keypad. And then I type in the next number, 995, and enter. And the answer is 1,870. I'd like to also show you the Google calculator. So I'm going to go to google.com, and in the search box, I'm going to type something like quick, 5 minus 2, 5 minus 4, I guess. Something quick. 5 minus 2, 5 minus 4, 6 plus 3, any quick little expression will resurrect your calculator. Now we're looking at the Google calculator. I'm going to clear it. And we were adding 878 plus 995 equals, and we get our answer 1,870. The Google calculator. You'll want to use it. It's free, and it's easily resurrected with just some quick little expression. So we'll resurrect that again. I'm opening my browser, and I want to go to google.com. In the search box, just type something quick, 3 plus 2. And it will resurrect your Google calculator for you. Clear, and then go ahead and enter your problem at hand. On page 10, we're looking at example 2, where we are to add 391 plus 1,276 plus 789 plus 5,498 equals, and my answer is 7,954. example 2, I have 10. I'm going to add 391 plus 1,296 plus 709 plus 5,000. Enter, and I get 7,004. So in your textbook, the author presents, or your ebook, your author presents the calculator table frequently, and I'm on page 10. And the discussion continues with adding whole numbers using your calculator with several examples and key press definitions. So please spend some time with the calculator corner on page 10. Get familiar with the Google calculator as it's free and it will suffice for use in this course. On page 11, we're introducing perimeter. The perimeter, the distance around an object, perimeter. So we're asked to find the perimeter of this object. We're going to add the length. So I'm carefully going to start at some location in equal distance. So the perimeter is equal to, I'm going to start with this length, 29 plus 19 plus 37 plus 44. I'm adding 29 inches plus 37 inches plus 4 inches. The units are all the same measurement. I'm going to add with my calculator to come up with 129 inches. The distance all the way around an object is called the perimeter. You might put a fence around your garden to keep the rabbits out. Putting a fence all the way around your garden, you're going to have the distance all the way around. The perimeter is the distance around. The next example is the Lucas Oil Stadium in Indianapolis. Has a unique retractable roof. When the roof is open, retracted. In good weather, creating an opening stadium. The opening approximates the rectangle, 580 feet long and 10 feet wide. We're supposed to find the perimeter of it. Well, now it looks like the stadium is open, and that opening, we have a shadow box here labeled. The opening area is 580 by 300. Approximates a rectangular object. So we want to find the perimeter. Now the perimeter is equal to the distance all the way around. So if this is 300 feet, this is also 300 feet on this side. And if this is 580 feet, this is 580 feet on this side. So I'm going to start with 588 plus 300 feet plus 588 feet plus 300 feet. And I've collected the lengths of all the sides of the object. Adding, I'm going to get 1,776 feet. So the perimeter, that is the distance all the way around the opening of the roof, is 1,776 feet. Notice that all measurements are the same, feet, so I label my answer also. On page 13, we have a couple of examples of objects. Find the perimeter of each figure. And in number 27, we have 19, 50, 23, and 40 yards as the distance all the way around. So I'm going to use my calculator and add the distance at 19 yards plus 50 yards plus 23 yards plus 40 yards is equal to 132 yards. Be sure to label your answer. In number 28, we are looking at an option and each side is labeled miles. So I have 2 miles, 15 miles, 13 miles, 8 miles, 10 miles, and 47 miles. So I'm going to start at some location and be consistent. 22 miles plus 14 miles plus 13 miles plus 8 miles plus 10 miles plus 47 miles. Enter. I get 114. Be sure to label by units, this time miles. And then find the perimeter of a standard hockey rink. Well, we have a diagram then of a hockey rink, and it's labeled the length is 200 feet and the width is 85 feet. So to find the distance all the way around, I have 200 feet by 85 feet. This will be 200 feet, and this will be a width of 85 feet. So I'm going to start in some location and be consistent. Pick up the lengths of each side, 85 feet plus 200 feet plus 85 feet plus 200 feet. Enter, and I get 570. I'm going to label the perimeter as 570 feet. Section 1.3. In section 1.3, we're introducing subtraction. Subtraction. And on page 14, we have a definition. Subtraction. The difference, A subtract B, is that unique whole number C, for which A equals C plus B. We see that 6 subtract 2 is equal to 4, because 4 plus 2 equals 6. So to subtract whole numbers, we can check by addition. So subtracting, I have 9,768. I'm going to subtract 4,320. I'm going to use my calculator and Google Calc. On my calculator, I have 9,768. Find your operator key for subtraction, which is your hyphen. Subtract 4,320. Enter. And I get 5,448. My Google calculator, I'm going to clear, and I have 9,768. I want to subtract using the hyphen 4,320 equals 5,448. Well, that we agree with our calculator and our Google Calc. And now we've been told that we can check by addition. So we check using our answer. 5,448 plus what we were subtracting, 4,320. And sure enough, we get 9,768. So to find the difference, we subtract and we check using the answer plus what it was we were subtracting to increase up to our original answer of 9,768. Let's look at example 2 on page 15. We're supposed to subtract 348, and we're going to subtract from it 165. This is an example of borrowing in longhand. I line up my placeholder significant columns. I'm going to subtract 5 from 8 and get 3. But 6 I cannot subtract from 4. So I'm going to have to borrow from the next placeholder. I'm going to borrow, reduce this placeholder by 1 to 2, and increase this by 10. So now I have 14, subtract 6 is 8, and 1 from 2 is 1. And then let's check. If I add my answer plus what it was I was subtracting, I should be back at the total that I was subtracting from. 3 plus 5 is 8. 8 plus 6 is 14. Carry the 1 to the next placeholder, and I get 1, 2, 3, 348, so I can circle my answer. Now on page 15, there is your Google calculator for subtracting whole numbers with a narrative and discussion on how to subtract using your calculator and significant key press. Example 3 on page 16. We have 6,246 and we're supposed to subtract from it 1,879. Longhand, I'm unable to subtract 9 from 6, so I borrow from the next placeholder, reduce that by 1 to 3, and I'll add 10 to 6 and get 16. 16 subtract 9 would be 7. 7 from 3 now. I can't do that, so I'm going to have to borrow from the next placeholder, reduce it by 1, and add 10. I have 7 from 13 would be 6. 8 from 1, I'm not able to do that, so I'll need to borrow from the next placeholder, reduce it by 1, and add 10. That's 11. I'm going to subtract 8, I'll get 3. And 1 from 5 is 4. I'm going to check my answer, 4, 3, 6, 7, plus what I was subtracting. 7 plus 9 is 16, carry the 1. 1 plus 6 is 7, plus 7 is 14, carry the 1. 1 plus 3 is 4, plus 8 is 12, carry the 1. And 4 plus 1 is 5, plus 1 is 6. 6,246, so I can circle my answer. With my calculator or Google Calc. 6,246, subtract 1879, enter. Oops, got turned on first. 6,246, subtract 1,879, enter is 4,367. Section 1.4 begins on page 19, and we're just going to go to the top of page 20 and introduce some terminology. I have 3 times 5 equals 15. This is called a factor in multiplication. This is called a factor in multiplication. This is my operator for multiplication. The numbers that you multiply are called factors. The result of multiplication is called a product. We note that there are different types of operators used to indicate multiplication.
we could have 3 dot is the same as 3 times 5 using our parentheses, the same as 3 times 5 using parentheses, and all equals 15. $734 times 5 with our calculators. 734 times 5. On our calculator, we're going to be using the X on your keyboard, probably the asterisk, to represent multiplication. So 734 times 5 is 3,670. And it would be the same for Google Calc. So you don't need to buy a calculator for this course. You can use Google Calc as a free calculator source. Now on page 21, you will have your Google Calculator with a narrative on multiplying whole numbers along with the indicated key press that you need to accomplish multiplication. On the bottom of page 20, we introduce the distributive law. Multiplication of whole numbers is based on a property called the distributive law. It says that to multiply a number by a sum, a times the sum, b plus c, we can multiply each add-in by a and then add. Thus, we end up with a times the sum, b plus c, is actually equal to a times b plus a times c. This is called the distributive property. Very important. You must memorize and understand. So I have something times a sum is equal to something times each item that we're adding. So I use the distributive law to distribute a times the first term to be a times b. I pick up my sign and distribute a times the next term, which would be a times c. Which is AB plus AC. Now let's try an example. If I have 4 times 2 plus 3, it should be equal to, according to my pattern, this is A's position, this is B's position, C's position. And I can expand that as A times B plus A times C. So A is 4 times B, which is 2, plus A is 4 in this example, times C is 3. Here we have 4 times 2 plus 3 is 5. Here I have 4 times 2 is 8, plus 4 times 3 is 12. Here I get 4 times 5 is 20, and 8 plus 12 is 20. So it appears that our distributive law holds true. Let's try 3 times 3 plus 4. Well, that's our A times B plus C
And our distributive law says that we can expand that as A times B plus A times C. A in this case is 3 times B is 3 in this case, plus A in our case is 3 times C, and C's position is 4. Patterns, so we're placing our pattern above and expanding. I have 3 times 3 plus 4 is 7. Here I have 9 plus 3 times 4 is 12. 3 times 7 is 21. 9 plus 12 would be 21. So it appears that our distributive law holds true. You'll want to practice the distributive law and make sure that you understand how it works. So here I have 3 times 3 plus 4, and I just distributed 3 times the first term in the parentheses would be 9, plus, pick up your sign, and distribute 3 times the next term, which is 12. And 9 plus 12 is 21. Now the distributive law, I have 3 times the quantity. So I'm going to take 3 times every term within the parentheses. Distributive is a large word. Think about in the classroom, if you were sitting here in front of me and we had a quiz. I would make sure that I distributed a copy of the quiz to everyone. I wouldn't skip anyone. I would be distributing the quiz to everyone in the class. Here, I'm just distributing 3 times every term within the parentheses. 3 times the first term, 3 times the second term, maybe there's a third term. I'm distributing 3 times every term within the parentheses. The distributive law. On page 22, we introduce the commutative law of multiplication. The commutative law of multiplication. The commutative law of multiplication says that A times B is equal to B times A. Now what happened? It looks like we changed the order. The commutative law for multiplication. Now this is for multiplication. It doesn't say anything about division or subtraction. This is talking about multiplication. Commutative law for multiplication. Now commutative, we have within that word commute. Our terms can commute. They can move around. 3 times A times B is equal to B times A. So let's do 3 times 4. A's position is 2 and B's position is 4. So B's position would be 4 times 3. A's position, which is 3. 3 times 4 is 12, and 4 times 12. Commutative law for multiplication. 3 times 4 is the same as 4 times 2. As long as it's all multiplication, the order of your terms can move around, switch. Let's try another one. 5 times 2 should equal 2 times 5. 5 times 2 is 10. 2 times 5 is 10. The commutative law for multiplication, the order of your terms can change, can commute. On page 22, we continue with the associative law of multiplication. The associative law. A times the quantity, B times C, is equal to
A times B times C. Now, what changed? Well, the order hasn't changed. It's A times B times C, A times B times C. But I did change the grouping. Associative law pertains to the grouping of our terms. Associative law, again, kind of a big word. Think of the associative law as how we associate. We're associating now in a class of mathematics. Later, we might associate in a group at bowling. We might associate in a group at the Minnesota West Commons. So we can group ourselves differently. And that's what I'm doing with my parentheses. I'm grouping my terms differently. Now, if we have A is 2 and B is 3 and C is 4, then on this side, A is 2, B is 3, and C is 4. I have 2 times 3 times 4 is 12. Here I have 2 times 3 is 6. What's left times 4? 2 times 12 is 24. 6 times 4 is 24. So it appeared that that worked. The associative law of multiplication. Our terms can associate differently as long as it's all multiplication. I don't see any division or subtraction. This is the associative law of multiplication. Our terms can group differently, but our answers will be the same. On the top of page 23, we have a professional pool table. The playing area of a pool table used in professional tournaments is 50 inches by 100 inches. Now, the playing area, that's the surface, not including the wooden support. There are 6-inch wide rails on the outside included in the playing area. Determine the playing area. Now we're talking about the area of the object. It's a rectangular object, so we have a width of 50 and a width of 50 inches and a length of 100 inches, so this side is 100 inches. Area is equal to the length times the width. Area of an object. Now, length times width. So the area of this pool table playing area is the length times the width. And they told us that the length is 100 inches and the width is 50 inches. Now I have my unit measurements here. Remember that in multiplication we can change the order, doesn't matter. So I have 100, I'm going to collect my constant values together and get my labeling items together. So now I have area is equal to 50 times 100. Fifty times 100 is 5,000. And inches times inches is inches squared. We can also label our answer as 5,000 square inches. A couple different ways to label. This is making use of our exponents. Remember, a base times a base. Here's our base. It's the same base times itself 2 times. In area, we always end up with square unit labeling.
On page 25, we have question number 37. It says find the area of each region.
The area, remember the area is the length times the width.
This object is 728 miles by 728 miles. So I have 728 miles for the length, and the width is 728 miles. So the area is equal to 728 miles times 728 miles. Area is equal to, I'm going to just gather my like constant in multiplication and my unit measurement. Area is equal to 728 times 728. And I get 529,984. And miles times miles would be square miles, or using exponents, miles times itself 2 times. Number 38 on page 25, I have a diagram. It's 129 yards by 65 yards. And it is a rectangular object, so my area is equal to the length times the width. Once I know my pattern, I can substitute the length is 129 yards times the width, which is 65 yards. Organizing, this is all multiplication, so I'll get my constants together, and then I'll get my units together. Commutative law of multiplication order doesn't matter. I have 129 times 65, and I get 8,385. And yards times yards would be square yards. And analyzing a diagram, find the area of the region formed by the baselines on a Major League Baseball diamond. So here we have our home plate, first, second, and third. From home to first is 90 feet, from first to second is 90 feet, from second to third is 90 feet, and from third to home is 90 feet. So the area is equal to the length times the width. The area would be equal to 90 feet times 90 feet. The area is equal to 90 times 90 is 8,100. And feet times feet is square feet. Section 1.5 begins on page 26. We're going to go to the top of page 27, and we're defining division. The quotient, the answer when we divide, the quotient A divided by B, where B is not 0, is that unique number C for which A equals B times C. This definition shows the relationship between division and multiplication. For instance, we see that 20 divided by 5 equals 4, because 20 equals 5 times 4. This relation also allows us to use multiplication to check division. So let's divide 16 by 2, or by 8. So I have 16 divided by 8. On my calculator,
16, use your division sign. Your key is the dot over a hyphen, dot, dot, divided by 2. Whoop, I say 16 divided by 8 is 2. Sure enough, it's 2. You can use your calculator or again, Google Calc. We're asked to check. Well, that'd be our answer times what we are dividing by, our divisor. 2 times 8 is 16, so you can put your answer. We might see 36 divided by 9. So again, 36, make sure you use your division operator on your device. Divided by 9 is 4. And we check by multiplication our answer 4 times the divisor, which is 9. 4 times 9 is 3. And circle your answer. Other important information on page 27. Dividing by 1. Special cases. Any number divided by 1 is that same number. A divided by 1 is equal to A over 1, which is equal to A. For example, 6 divided by 1 is 6, and 15 over 1 is 15. So 7 over 1 is equal to 7. 7 divided by 1 is equal to 7. Dividing a number by itself. Any non-zero, remember that, non-zero number divided by itself is 1. A divided by A is equal to A over A, which is equal to 1, as long as A is not equal to 0. For example, 7 divided by 7 is 1, and 22 over 22 is 1. So 22 over 22, 22 goes into 22 once. 7 divided by 7 is 1. Any number divided by itself is equal to 1. So another name for 1 could be 7 over 7, 22 over 22, 15 over 15, and so on. Oops. I'm gonna have to show you that page again. Okay. So any number divided by itself is another name for 1. 7 goes into 7 once. Another name for 1 would be 7 over 7, 22 over 22, or 15 over 15. Another name for 1. And then most important on page 27 is 0 divided by any non-zero number is 0. 0 divided by some other than 0 is 0. For example, 0 divided by 14 is 0. 0 divided by 3 is 0. If I have nothing and I divide it by some number, it's still 0. But on page 28, our most important, we must memorize exclusion. We have to exclude division by 0. Division by 0 is not defined. Any number divided by 0 or A over any 0 number is not defined. For example, 16 divided by 0 or 16 over 0 is not defined, and we use ND quite often, and you will see that at my math lab, ND abbreviated for not defined. So with your eagle eyes,
over 16 equals 16 divided by 16, which is another name for 1. Any number divided by itself is another name for 1. 16 divided by 0 is undefined. We cannot divide by 0. You must memorize that. So then we think about division. If I have 6 goes into 22, which could be the same as 22 divided by 6 or 22 divided by 6 using different symbolism. Well, this is longhand division, so I'm going to go 3 times 6 is 18 and subtract to find the difference. To borrow, that'll be 12, subtract 8 is 4, so I have a remainder of 4. Well, that was longhand division, and that gets tedious, and I can often and easily make mistakes. So let's check with our calculator. 22 divided by 6, enter. I get 3.67. Now, your calculator and Google Calc will display your answer in decimal form. So decimal format or decimal notation. And we really don't want this decimal part. We want a remainder. We want the integer remainder, the whole number remainder. But our calculator does help us out because it gives us at least 3 times 8, 3 times 6. So 3 times 6 equals 3 times 6 is 18. And I know I have a little bit left over. I'm not quite at my dividend. So the difference, 22 minus what I have, the whole number times a whole number, I get 22 subtract 18 is 4. That's my remainder. So my answer is 3 with a remainder of 4 using my calculator. Now how do I check? I have 3 times 6, which equals 18, plus that little bit of a remainder. And 8 plus 4 is 22. So 6 goes into 22 3 times plus a remainder of 4. That gets a little tricky, so we'll do another one. This is example 2 on page 29. We have 4 goes into 3, 4, 5, 7. Now I could work that longhand, but that does and can be tedious, and I can easily make a mistake. So let's use our calculator. And I have 3,457 divided by 4 equals. And it says I have a whole number plus a little bit, so I know I'm going to have a remainder. There's a decimal point there. I know I have a remainder, but I have 864 as a whole number. 864. Now to check, I have 864 times 4. 864 times 4 should get me pretty close to my 3,457. I actually have 3,456. Now to find the little bit that's left, I'm going to subtract 3, 4, 5, 7. From my dividend, I'm going to subtract what I have so far with my whole numbers times my divisor. 3, 4, 5, 6. And I have a difference of 1, so I have a remainder
of 1. I can check 864, the whole number, times the divisor 4. 864 times 4 is 3,456. But I had a remainder of 1, so I need to add that. Plus your remainder, and you get 3,457. So our answer checks. We can circle our answer. Now on page 330, in your e-text, you'll find the calculated corner for the narrative on dividing whole numbers and the key press sequence. You should check and experiment with some of these examples. Let's try one more. Example 4 on page 31. 7 goes into 6,341. Well, I could do this longhand, but that can be tedious and I can easily make a mistake. So let's use our calculator. 6,341 divided by 7, enter. I get 905 plus a little bit, 0.86. So I know I have 905. So 7 times 905, my whole number, my calculator, 7 times 905 is 6,335, which is close to my dividend, but not quite, because I know there's plus a little bit. So I'll have to find that difference. 6341, subtract what we have. And I have to borrow, that goes to 3. 11, subtract 5 is 6. So my remainder is 6. And I can check. I have 905 times 7. 905 times 7 is 6,335. But I have a remainder, so I need to add that. Plus 6, and I get 6,341. And sure enough, that is my dividend, so I can circle my answer. On page 35 and 36, you'll find review problems from sections 1.1 through 1.5. You're encouraged to work some or all of those to refresh the topics discussed in these sections. We will continue with our next video. For now, I wanted to point out to you that there are period names beyond thousands, millions, and billions. In fact, next we have trillion, quadrillion, quintillion, sextillion, septillion, octillion, and so on. And these period names continue forever. So now return to D2L Brightspace, our course homepage, and find all details regarding homework, assignments, tests, and due dates for this chapter. And thank you very much.